Can you see the full slide of my presentation?
Yes.
Yes.
So, the objectives of Pilot 2 is to assess the risk of a power transmission line in a Nordic climate and to investigate the potential use of adaptation measures such as carbon FRP, fiber reinforced plastic plates or high-strength steel, and to evaluate engineering and social risk and impacts related to power outages. So, some background on the risk of a structure. The risk is actually the probability of failure of a structure given its characteristics and the hazard of its location. And it has two components, the fragility, which is the probability of failure of the structure under a specific level of one or more intensity measures, and is structure specific, so it depends on the structure and its characteristics. And the hazard, which is the probability of occurrence or exceedance of specific intensity measures. The selected line is an 8-kilometer long line in East Finland, and the climate hazards that are considered are extreme wind speed, ice accretion, and the combination of the above. Here as we have depicted the profile of the line, and the line consists of 35 towers. 32 of those are of suspension type and 3 are tension, and based on its configuration can be considered as a straight line, and also no main difference in heights between adjacent towers is observed, so we make an even level assumption. The type of towers used for this line are Guyot Porta towers, relatively short because its maximum length is height is up to 24 meters. They carry 3 phases of 2 bulk conductors and 2 earth wires, which are slightly different. And also each tower is supported by 4 pre-tense guys, and the rolling span of the line segment is 246 meters long. We selected to analyze one tower of the line, and the type of tower is support, because support are the weakest parts of transmission lines, and if they fail, they lead to a progressive failure to the adjacent towers, and the whole line will eventually fail. We picked a tower with height of 18 meters because this is the most used height in that line. We modeled the tower in OpenSense software, and we decided to have a simplified model in order to reduce computational cost. Simplified model means that the trusses were modeled as built-up member as per Eurocode 3. In these graphs, we show the conductors and earth wire strength for various wind speed and icing combinations. We can say that all conductors and earth wire can step up to 75 to 8 millimeters of ice before reaching this rated strength. So for icing scenarios of more than 75 millimeters, we can consider that the earth wire or the conductor has been broken, and the tower will fail due to the unbalanced load caused by the broken conductors or earth wires. We considered several versions of the tower. The first one is the as-built, which means that we used all the specification and the properties of the design, and we consider also a steel class of S355. The second version is the deteriorated tower, which is where we assume a uniform loss of 0.5 millimeters per side in each cross section. And then we consider adaptation options, 2 different types of adaptation options, the use of FRP plates on the corroded tower, and also 2 scenarios, single strengthening, where we apply FRP plates only externally at the members of the tower, and double strengthening, where we apply FRP towers both externally and internally. And also for the HSS scenario, we consider that the tower will be replaced by a new one built by a steel of higher strength, and especially a class of S460, and we consider 3 different scenarios. In order to estimate the fragility of each of the towers considered, we perform multiple nonlinear dynamic analysis of various combinations with speed and ice thickness. Of course, in order to reduce the computational cost, we picked specific ice thickness scenarios, and especially 4 ice thickness scenarios. And I should mention that for some towers, they result in failure before reaching 75 millimeter of thickness. And for the intermediate ice values, we use linear interpolation. The wind direction was considered always perpendicular to the line. Of course, this might not be 100% accurate, but it's the worst case scenario. And the probability of failure for each combination with speed and ice thickness was estimated. And on the probabilities of failure, a log normal fit was performed in order to estimate the parameters of the fragility curve, which are the median with speed of failure and the dispersion. And all this process was performed for all the tower versions, the initial, the corroded, and the versions of the adaptation measures. And here I present some indicative fragility curves. As you can see, some interesting conclusions can be made. First of all, the probability of failure for the rate for the same with speed increases as ice thickness increases, and this is normal since we have additional weights due to ice, and also the area of projection of is also increased, so the wind force are increased. And the most interesting is that the different adaptation options result in different wind speeds of failure, median wind speeds of failure, so different fragility curves. Regarding the hazard, as I said, we use data provided by FMI. Marco also described those climatic scenarios, and we use 6 climatic models, and we assume a general life extreme value distribution.
Is this the age twin predicted data?
Yes, I think that regarding the future scenarios, yes. And we assume the generalized extreme value distribution for wind speed and ice thickness. And in order to estimate the risk for each tower version climate model, we applied this equation, which takes 2 components, the probability of failure, which is fragility, and the hazard, which are, in our case, the probability density functions of wind speed and ice thickness. And we are able to estimate the annual probability of failure. And by taking the reciprocal of the annual probability of failure, we estimate the return period, which is a value that it is used by engineers in design. And these are the results in terms of the probability of failure for all the scenarios of towers considered and the climatic scenario. And I have put a dot line with in the 50 years, because 50 years are usually the design value accepted by codes. And as you can see, the results are sensitive to the climate model selected, and the EC Earth model seems to be more conservative than GFDL models, so especially when future periods are considered. So the outcomes of Pilot 2 work in risk-adapt. As expected, the corroded tower shows greater probability of failures and shorter return periods than all the other towers in all climate scenarios. However, we should mention that in most climate scenarios, the return periods are larger than 50 years, so they can be accepted. Some climate scenarios show that the risk of failure might be decreased in future years, a fact that could be attributed to the low rising loads that are expected due to temperature rise. So climate change may have a positive effect in our case. And we should also notice the large variability in resulting risk between various climatic models. So caution is needed when you select and apply a climate model. And all the adaptation options achieve a restoration to the performance of the initial tower, especially the FRP scenarios achieve performance close or even better than the initial tower. The high strength steel scenario 1, we should note that shows risk results similar to the initial tower, so it means that we will have a restoration of the initial tower, although it uses more than 10% less steel. So this might be beneficial in terms of economic cost and also environmental impact. HSS scenario 2, although it shows larger risk than the initial, it still have acceptable return periods, so they can be considered as a potential alternative option to HS scenario 1. And the HS scenario 3, which is a scenario with the less material, may not lead to significant improvements because the risk results are close to the one of corroded, so the option might not be efficient. So this is the work performed on risk analysis of the transmission towers of Finland. And it's the pilot 2 of the risk adapt.
As an introduction, I'm Carlo Cintolesi, researcher in the group of atmospheric physics of the University of Bologna, led by Professor Silvano Di Sabatino. And I will start, and then I will leave the floor to Vasilis Kalidromitis from Technic on the structural analysis, while I'm mostly focus on the estimation and analysis of wind and wind-driven load, and in particular to the building of Cattinara Hospital that we'll introduce later. So just a short introduction of the motivation. The actual climate change trend shows that extreme weather events will increase in frequency and intensity in the future. So, and also the temperature and the heat waves are the most visible effect, but also strong storms events will be more frequent in the next decades. So there is a need of improve our ability of estimate the atmospheric load that is given by wind and wind-driven rain on buildings under extreme events. And to do that in a more realistic and effective way. To address this challenge, we use a numerical simulation, and in particular, some numerical techniques of the computational fluid dynamics, which use a very high resolve numerical mesh, which is able to reproduce in details the wind field, the pressure gradients, to the very small scales of motions. That is the important one for estimating the atmospheric load on the building facade. This challenge is addressed in Risk Adapt on the case study of the Cattinara Hospital. Cattinara Hospital is the only public hospital in the Trieste city, which is located in the north of Italy on the Adriatic Sea. And it has been chosen because of two main characteristics of this pilot. The first is that the hospital is built on the top of the hill, so it's particularly exposed to the atmospheric wind and rain. And it is composed of two relatively tall towers, let's say talls for the European standards. The second is that the entire area of Trieste is characterized by a particularly and very intense wind, which is called the Bora wind, given that it has a topographical genesis coming from the Karsic plateau of Slovenia, and that can reach a very high intensity and gusts that can be of 130, 150 kilometers per hour, giving many problems to the city infrastructures and for the most intense events also leading to loss of functionality of many infrastructures. So we select these case studies, and in particular we focus on a particularly intense event that was the 11th of February of 2012, in which it was measured a record of wind speed. And so we focus on this case and we reproduce numerically these events. The simulation approach we use, basically we reproduce in details the topography of the site and the main buildings of the hospital structure, which is composed of several low buildings and the two main towers of the hospital itself, and some other ancillary buildings in the neighborhood. So the computational domains will account both from the topography and the detailed building structure. Some very short technical details. We use a Reynolds average Navier-Stokes approach using a K-epsilon turbulent model, which is quite well assessed and standard. But we apply this methodology to a very fine mesh that counts around 5 million of cells, and near the surface of the buildings, we have cells of half meters, of the order of half meters to the 10 few centimeters, let's say. This allowed us to have a very fine resolution of the wind stress and the pressure on the building facade and around the buildings. As an inflow condition, we use a uniform wind, which is considered from our side as the worst condition, with an intensity which is the maximum registered for the events of the February 2012. The simulation results shows first many things, but here I will summarize just two main results. First, that the topography of the site play an important role in modifying the profile of the wind impacting the buildings. For example, there is a valley between just upwind to the hospital site, which alter the overall circulation, increasing the velocity on the surface near the ground, and also the turbulent kinetic energy, so inducing more turbulent and intense wind near the ground. And so this leads us to consider that the topography around the buildings should be taken in consideration, because can largely alter the impact of the wind on the building. Then we also analyze here is shortly reported the analysis of the wind circulation around the buildings. And also in this case, we have noticed that there were some channeling effect and some recirculation regions that somehow play a role when it comes to estimate the load, the pressure load on the building itself. But for the sake of brevity, I will go directly to the results, which is of more interest for the RISC-ARAT project, which is the load on the building facade, estimate through the pressure coefficient and the pressure distribution. So here you can see a three-dimensional visualization of the pressure on the facade of the Cattinara Hospital. And we can see that the facade mainly impacted by the are that one directly exposed to aligned to the main wind direction. And the building which is on front side is much more impacted with respect to the building, to the towers, which is on the second stage. Based on this result, we also perform a parametric analysis varying the intensity of the atmospheric wind, not changing the direction, but just the intensity. And this allowed us to develop some simple semi-empirical relation which link the intensity of the impacting wind with the pressure that can be measured, that can be estimated on the facade of the buildings on different locations, which we consider as the most important to assess the structural analysis for the building. So this is just a short summary of our research. This output has been given to for the structural analysis carried on by Vasilis Kalidromidis, to whom I leave the floor.
Okay. I am Vasilis Kalidromidis. I'm a civil engineer from Technic, and I will show you some slides concerning the structural evaluation of the Katinara Hospital. Next, please. Katinara Hospital is located at about 10 kilometers from Trieste center, 250 meters in height, and according to the Italian rules is classified in class 4. It is a building of strategic importance. We make a reassumption of what it happened to this pilot, because it is very interesting as to have as guide. Original design started in 1969 and was foreseen in thick beams and slabs, rigidly connected to the vertical columns, resulting, of course, in a typical frame structure. At the time of the construction, Katinara site was not yet classified as seismic, but in 2010 is classified in category 3, which is low seismicity. So the above fact, and also the fact that the wind load, the design wind loads changed by the Italian norms and laws on 2008, means practically quite 20 years after the design. And the exceptional wind forces in February, as we saw before, of about 180, 200 kilometers per hour gas, imposed to the stakeholders to require a new evaluation of the seismic capability and, of course, of the structural vulnerability. The design review showed that the towers, which are about 60 meters tall, had some problems. The first problem, the important first problem, they was too close together, because we have, practically there are 4 towers, 2 shape L towers coupled, and this coupling put together, they were too close together, because of course before, when they were designed, seismic capability was not taken into consideration. And so in order to avoid pounding and hammering according to the design rules, they were provided fluid dynamic designed shock transmitters. Next, please. To avoid, of course, this phenomenon. So definitely all these changes of the codes and also the seismic approach imposed practically the refurbishment and the upgrade of the structural capability of the building. So since 2017, and following also other medical necessity, the hospital has been upgraded, spending quite 140 million euro. And it is to say that the towers resulted in an excellent behavior during a recent catastrophic seismic event that occurred in 2021 in Slovenia city of Petrinja, far away of about 150 kilometers, but 6.4 Richter of grade of seismicity. The complex cover actually 110 square meters, and at the end will be approximately 165 square meters. So all these impose to make, to adopt a methodological approach in risk adapt as follows. First of all, to propose steel bulk corrosion models and concrete degradation models to predict the evolution of the mechanical characteristics of the materials in order to provide the required quantitative input for structural assessment. The second was to develop the structural model that was based on the as-built drawings, because the section of the piers were not changed, but the reinforcement inside were changed. And this was done also by laboratory and in situ test. The third thing was to define how much we are confident with the knowledge level and the degree of the structure. So with this kind of approach, we ran the risk adapted finite element model in a real situation in order to evaluate the internal forces and the structural vulnerability, to analyze the result and identify the critical section, and finally estimate the safety factor in the eventual damage stage. Some of the results are summarized in the following slides. Next, please, Carlo. Thank you. This was the model built for risk adapt. Of course, this model is according to the drawings received by the stakeholders and some other structural elements that were analyzed through the original design drawings and the revised design drawings. Next, please. This is the effect of the design wind load to Katinara Hospital, and we can see the displacement of the nodes. The maximum displacement at the top of the building with the design wind load, of course, is about 22 centimeters. Next, please. And these are the shape of the bending moments, always according to the design wind load of 30 meters per second, which is imposed by the Italian rules. Next, please. Now, of course, in order to establish the structural vulnerability, we have to make the check of the sections, and here are some examples. We have the results of the safety factor for column 3, level 1, which is the base column, and have a safety factor of 1.59, and the level 6, which is safety factor 2.66, with a design wind load velocity of 30 meters per second. Next, please, Carlo. Thank you. Now, the model has run for all the nodes, for all the column nodes that were the critical points of the structure, and the fragility of the structure was estimated by iteratively changed wind loads and moment curvature combinations. Moment curvature for respective return periods and confidence factor was evaluated in 3 damage stages: moderate, severe, critical, collapse or critical. Fragility cues for each damage state considered were developed assuming a log normal distribution but it is important to see what was found as annual probabilities of occurrence for each damage stage. So we have for a damage state, for a moderate damage state, we have approximately 3.76% of annual probability. For severe damage state, 2.97%. And of course, for critical annual probability, it is only 1.7%. Next, please, Carlo. Now, what are some findings we found according to these studies? According to the studies, we found that topography, also mentioned before by Carlos' presentation, is the topography location of the building. At the time of the design was not taken into consideration, and according to our estimations, this can produce an increment of 10 to 15% as occurred in Katinara Hospital. A second remark is that Katinara Hospital is a strategic infrastructure, and the return period of 50 years for the design wind load is enough for the estimation or needed to be increased. This is a further question that can be made, and the actual Eurocode loading is under revision, and of course the national codes must be adopted in accordance. I have to say also another thing, because the previous slides you saw the safety factors were made according to a real condition, not to the imposed condition of the norms. Because in the design process, there are uncertainties inherent with the value of the loads and the material properties, which impose the introduction of a favorable situation through specified factors. So we have an extended margin of the values that use the probably simplified and approximate analysis procedure in the design. In the real structural evaluation, a different approach could be used from that applied in the design, and can done more precise results according to the position of sensors in sensitive location. This is actually also what it happens to Katinara Hospital. The stakeholders use to put sensors in order to have the real situation during the whole life of the structure and the real situation of the behavior of the structure. Next, please. So, here we can see an approach which means to put some sensors in the sensitive locations of the building in order to evaluate the axial strains and the curvature through the strain sensors. This gives us the possibility to have the real, according of course to the constitutive laws of the material, and to have practically the real situation of the internal structural capacity and the internal and the structural demand of the concerned concrete sections. So we have the real situation that is very easy to get according to this position of the sensors. Next, please, Carlo. Thank you. I think we finished. Thank you very much.